Okay, so welcome back. And now that we've done an example of showing how to find the right endpoint approximation and the left endpoint approximation, let's talk about, well, we can see from the previous example that when we have a small number of rectangles, the approximations, whether you use the right endpoint approximation or the left endpoint approximation, isn't all that accurate. Okay, so now what I want to go over in this video is show how the number of rectangles affects the accuracy of the approximation. So I'm going to do an example. Now I'm not going to do the whole example because again some of this gets you'll have to do in the calculator. So I'm going to do the n equals 4, but then I'm going to show you the approximation, and I'm only going to do left endpoint approximation for this one because again the same conclusion can be shown with right endpoint approximation. Okay, so you'll see as the number of rectangles increases, what happens to our approximation. Okay, so let's start with the first one, n equals 4. So again, let's get our delta x. So delta x is going to be again 2 minus 0 over 4, which is going to be equal to a half. Okay, b minus a over n. And so that means that our intervals is going to be what? Our interval is going to start with 0 and then go up by a half. So it's going to be 0 to a half, and then a half to 1, and then 1 to 3 halves, and then 3 halves to 2. Okay, which is where we start. So we got 4 subintervals, 1, 2, 3, 4. Starts at 0, we ended at 2, we're good. Okay, now, with the left endpoint, what do we get? Well, L sub 4 is equal to what? Oops, let me write out the summation. So this will be the summation for I equals 1 to 4 of f of x sub I minus 1 times delta x. Okay? And so now I'm going to say, okay, this is going to be f of 0 times delta x plus f of a half times delta x plus f of 1 times delta x plus f of 3 halves times delta x. Okay? And so now what I'm going to do is just simplify this, and I'm going to plug and chug, right? So f of 0 gives me 5, right? So I'm just going to calculate this. So at 0, at 0, this is going to give me negative 1 plus 3. So this is going to be 3 times a half. Plus now at a half minus 1 is minus a half, so that's going to give me a negative 1/8. Yeah, negative 1/8. Right? So 1/2 minus 1 is negative a half, so it's going to give me negative 1/8 plus 4, which is 3, and yeah, 3 7/8. So it'll be 3 7/8 times a half plus 1. So 1 minus 1 is 0, so that's going to give me 4. So 4 times a half. And then finally, 3 halves. So 3 halves minus 1 is going to be a positive half, which is going to be positive 1/8, which is going to give me 4 1/8 times a half. Okay, so now if I put this in my calculator, I'm going to get what? I get 7.75. Okay, Now, that's the approximate area based on 4 subintervals. Now, what if we double it to 8 subintervals? Now, I'm not going to go through the calculation, but I encourage you, for practice, do it. Okay? 8 isn't too bad. 32 if you have time, but I wouldn't do 32 unless you really want to see if you get the correct answer. Okay. So with L of 8, oh no, hold on. This isn't 7.75. I get here, where's it at? 7.5. Wrote down. 7.5. Okay, now, okay, so now, with 8, you get L sub 8, which is equal to 7.75. That's the one that's 7.75. Okay? Now notice that delta x for 8 is going to be 1/4. So now all the intervals are split in half, right? And then for n equals 32, L of 32 gives us 7.9375. So it seems, now just looking at this, just looking at these numbers, it seems like what's happening here, as the ends get larger and larger, as the number of rectangles gets larger and larger, it seems like the area is heading towards 8. Okay? So it seems like there's a limit. Limit. So we're going to talk about using the limiting process. Hey, what happens? What's the limit of this thing as n goes to infinity? So hold on to your seats. Okay, have a great day.